Hey everybody, I wanted to spend a little bit of time talking about question 15.43 and in Braunlome Burston. This is not only is it a calculate the Q, but it's also concepts behind the reaction quotient. So I have taken this and I've copied this over into my notebook, and we can work on this problem right now. So before we get started, if we read the problem, it's giving us a value for the equilibrium constant. And so then parts A, B, and C, it gives us a mixture of each of those gases, and then we have to decide if it's at equilibrium. Well, the concept here is that if it's at equilibrium, the Q is going to equal K. And so we're going to calculate Q for each one of these things because that's how we know. So a Q, reaction quotient, is kind of like calculating the equilibrium constant, but at any time. It's just a numerical version of the law of mass action is what it is. And so remember that K is also a specific reaction quotient when the reaction is at equilibrium. So that's another way to look at it. But the point is, I guess, is we're going to have to calculate Q, so we're going to need to write the formula for Q. So Q is going to equal products over reactants. So it's the concentration of carbon monoxide, okay, raised to the first power. We can put the first there, or we don't have to, times the concentration of chlorine gas, raised to the first, all over the concentration of, I believe the name of that compound is phosgene, COCl2. I may be mistaken, but okay. So we're going to use this. We're going to use this equation for each part A, B, and C. Okay. So for part A, the concentration of CO. So for A, it's Q is equal to 3.3 times 10 to the minus 6 times 6.62 times 10 to the minus 6. I'm writing big, I guess, but that's okay. And then the concentration of COCl2 is 2.00 times 10 to the minus 3. Okay? So when we put that into our calculator, we get 1.10055 times 10 to the minus 8. So it's 1.1 times 10 to the minus 8. So we look and it says that K is 2.19 times 10 to the minus 10. So is it at equilibrium? No. But then it says, what direction does it need to move in order to reach equilibrium? So again, I love, when I do these problems, I love to just analyze it mathematically. I don't like to memorize that if Q is greater than K, it's got to shift one way or the other. Like that kind of defeats the beauty of chemistry. So, so this number, if we're comparing it to K, Q needs to decrease. Okay, so Q needs to go down. So in order for Q to go down, that means the products has to go down and the reactants have to go up. Well, the only way for that to happen is for this to shift toward the reactants. I almost said products there. Okay, so that's the only way that happens, because remember, Q is equal to products over reactants. So the products have to go down in order for the value of Q to get smaller. That makes the reactants go up. So that means when you have a reaction, reactants yield products. The reaction has to shift to the left or toward the reactants. Okay, so for part B, now we're just going to lather, rinse, repeat, I guess. So for part B, again, it's Q equals CO, the concentration of CO times the concentration of Cl2 over the concentration of COCl2, and then we're going to look up what those concentrations are. So I've just plugged in the values given in part B of this problem. And now it's a matter of just plugging it into the calculator and seeing if Q equals K. And we get that Q is equal to 5.5 times 10 to the minus 12. Okay, so now Q in this case is less than K. So now the opposite of our analysis in part A is true. So now we want Q to get bigger. So if we want Q to get bigger, remember Q is products over the reactants. So that means the products has to get bigger and the reactants has to get smaller. So when you have a reaction where the reactants react to form products, in order for the products to get bigger, we need to form more of that. So this reaction is going to shift to the right. Now my prediction, without doing this problem, is that part C is going to be where Q is equal to K, but I don't know. We'll find out. So let's do this. I deleted everything just to make it easier for me to be able to read the problem here. So remember, it's the concentration of CO over the concentration of Cl2 over the concentration of COCl2. Okay, and this is, again, those values are right there. So Q equals, notice that both of these are the same thing, so it's 1.48 times 10 to the minus 6 times 1.48 times 10 to the minus 6, and then we get that over 0.01. Again, we plug this into our calculator. When you do that, you get Q equals 2.19 times 10 to the minus 10. And we look up at the problem, and just like I predicted, in this case, Q equals K, so this reaction is at equilibrium when you have those conditions. Okay, so that is question 15.43. A little bit of equilibrium calculating and a little bit of reaction quotient stuff. Okay, have a great day, everybody.